Morning all. We're going to have a good day today. I love testing stuff. And we're going to test this IGBT. It's a single IGBT and it is part number CM600HA 28H, manufactured by PRX. Now, this looks like a very complicated setup, and it kind of is, but when you see it on paper, you'll say, oh, that's simple. Now, I'm using this Victor function signal generator, model number VC2002. The reason I've gone to this function generator is because the BNC jack on my old function generator, it's come undone. It don't work no more, and I can't figure out how to take the function generator apart to replace that connector. So, one of the things that this function generator cannot do, it cannot offset above or below 0 volts. And so, when I want to drive into a circuit like what we're going to do here, we're going to take this function generator and we want to drive into the input LED of an optocoupler. I don't want to go negative. I want to stay on the positive side. I want a square wave of 0 volts to 5 volts peak. Not 5 volts peak and minus 5 volts peak. I don't want that. So I made this offset adjust box right here. There's an operational amplifier, and the frequency comes into the box, and the output is adjustable with this potentiometer right here. To power up my offset adjust circuit, I have this plus or minus 15 volt DC power supply going to these screws. I'm using screws to clip onto. So here's plus 15 volts DC ground and minus 15 volts DC, and that powers up that operational amplifier circuit. I'll show you that schematic so you can make one of these if your function generator does not have offset adjust. Here's the frequency in from the function generator. Here's ground. This ground and this ground are tied together internally. And then here is the frequency out that's been offset adjusted. Now let's go over to the oscilloscope and you'll get to see my box in action. First we'll take a look at what the function signal generator is outputting, the frequency above and below ground centered around 0 volts. And then we'll take a look at the output of my box and we'll set up a 0 to 5 volt peak square wave with my offset adjustment circuit. Here we go, let's get close. We are looking at the output of the Victor function signal generator. And here we have a peak of plus 10 volts and a peak of minus 10 volts centered around ground. And right now we're running close to 175 hertz. Let's change the waveform. There's a triangle wave, a sine wave, and our square wave again. I can change with the function generator. I can change the frequency. There, the frequency is slowing down, speeding up. I can change the amplitude. And I can change the duty cycle. Let's go back to 50% duty cycle. That looks like it right there. But the one thing I cannot do is I cannot raise this waveform above ground or below ground. It always stays centered around ground. Now let's look at the output of my offset adjust circuit. Moving the scope to the output, and here we have our square wave again. It's a little bit lower in amplitude. That looks like about plus 8 volts and minus 8 volts thereabouts. Now watch what I can do with the offset adjust circuit. Look at that. I can move that waveform above and below ground. Now let's lower the amplitude and we'll make a 5 volt square wave. Let's go so that we sit right on top of ground. We have to lower the amplitude a little bit more. Raise that amplitude just a skoshie bit, and there is our 5 volt peak square wave with my offset adjust circuit and the Victor function generator. Isn't that amazing? Now that we have a 5 volt peak square wave, we'll connect it to the input LED of the optocoupler that we're using to separate the high voltage side from the low voltage side. We'll disconnect our oscilloscope. Let's move this over here. And we'll connect the ground of the function generator and offset adjust circuit to the cathode of the input LED, and we'll connect the output of the offset adjust, that's our 5 volts peak square wave, to the current limiting resistor going to the anode side of the input LED. Now, let's connect ground of the oscilloscope to the bus capacitor ground, and we'll connect the oscilloscope probe to the collector of the IGBT. Now what we have on this side of the optocoupler, this is on the output side of the optocoupler, it's driving into an NPN transistor, this tip 121. The collector is connected to the gate of the IGBT through this yellow wire right here. And the emitter is connected to the bus ground. We'll call this bus ground right here. I have a 15 volt power supply right here that is powering up this little circuit right here, providing the drive into the gate of the IGBT. On the variac is connected to the bridge rectifier right here, and the output, the positive and ground, bus ground of this bridge rectifier is going to 2 series bus capacitors, and they're rated at 3300 microfarad at 450 volts. They're wired in series. This is our load resistor. So we go from the positive side of the bus capacitors into the light bulb, and the other side of the light bulb comes back to the collector of the IGBT. So that this is our load in the collector of the IGBT. Let's apply 15 volts to our transistor circuit that's driving into the gate of the IGBT. Now we'll plug in the Variac. The Variac has come on. And look, we have a waveform. We'll get close to that in a little bit. We'll change to times 10 here. There we go. And as I increase the AC into the bridge rectifier, the DC is being applied to our load. Our IGBT is being switched on and off by the function generator and the offset adjust circuit driving into the optocoupler LED. The output of the optocoupler LED is being turned on and off, which in turn is turning on and off the NPN transistor and turning on and off the gate circuit. That's amazing. I'm going to move the camera over there so you can see the scope, the waveform on the oscilloscope. Our oscilloscope is set to 50 volts per division. And right now I'm increasing the Variac's AC voltage into the bridge rectifier, the bus capacitor setup. We're raising the voltage across those bus capacitors. Right there is 100 volts peak. So that IGBT is working. We have a good IGBT. That's an amazing circuit. When I get to the house, we'll talk about my drawings so that you can set up this test circuit right here. There you go, all. That's how you can test an IGBT. Oh, a couple of things. Why did I use an optocoupler to separate this low voltage side from this high voltage side? The number one reason I do that is because if we had a problem with the IGBT, a lot of times when they fail at the high voltage side, they'll shoot through the gate, or if you have a power transistor, they shoot through the base, and they destroy the driver circuit. So that's fine, but you don't want this high voltage to go back to the low voltage side if it shoots back up through the gate. So the optocoupler allows you that safety. Everything over here will get destroyed, but everything over here will survive. And if you had, for instance, a microcontroller driving into this transistor circuit right here to switch that gate on and off, and we didn't have any optocoupler isolation, your microcontroller would not live. You'd look at it, why does my microcontroller have a hole in it? The offset adjust circuit. Amazing circuit. You'll have a lot of fun building this. To begin with, let's go over the supply requirements for this operational amplifier. I used the TL071 ACP in an 8-pin dip package. That's this IC right here and right here. Pin 4, VCC negative, minus 15 volts DC from an external power supply. VCC plus, plus 15 volts DC from that same external power supply. And these grounds of the function generator and of the load being whatever you need to drive into, of that same external power supply. The operational amplifier circuit is set up as a inverting amplifier with a gain of 1. Here's the feedback resistor, 100 kilo ohms. The input resistor, 100 kilo ohms, that the function generator is driving into. Now, when the function generator is positive, the output is negative. And when the function generator input to this circuit is negative, the output is positive. That's why they call it an inverting amplifier. To provide the offset to this circuit, we have a 100 kilo ohm multi-turn potentiometer whose wings are set to plus 15 volts DC and minus 15 volts DC. The wiper of that potentiometer is connected to the non-inverting input of this operational amplifier, so that if we have a sine wave or a square wave or a triangle wave, if we centered that potentiometer so that we had 0 volts on pin 3, reference to this ground right here, the external power supply ground, the external power supply ground, the output would be centered around 0 volts. But when we increase this positive voltage, when we increase this potentiometer so that we have a positive voltage right here, reference to that ground, that external power supply ground, we raise this voltage out here. And when we go more negative, we go more negative out here. So we can swing that output positive above ground or negative below ground based upon this potentiometer's setting. The output of the operational amplifier is driving into this circuit right here. Here is our base resistor, 10 kilo ohms, and it is driving into the NPN or PNP transistor based upon whether we're positive or negative at the output here, or whether we're above ground or below ground based upon that potentiometer. This is a totem pole setup. And you'll see this a lot on the output of these TLO 71 ACP operational amplifiers, this very circuit right here. But I wanted to bring it out with a 2N3904 and a 2N3906 NPN and PNP transistors to provide more current drive into the load instead of relying on the output of this operational amplifier, which is much lower in current drive capability than this circuit right here. Don't forget your diodes. Your two diodes provide crossover distortion correction. If we on the output are below the diode drop of our base emitter junctions, that transistor is not conducting, and that's called crossover distortion, and these two diodes, they correct for that. Now here's our switch to turn the output of this complete circuit into the load. The load being whatever you want to drive into. I have a resistor symbol of RL. But you saw in the video that we drove into the input of an optocoupler. So our load could be an LED cathode junction. But this allows us to set up that function generator from sine wave to square wave, set the point right here to square wave of 5 volts peak from 0 to 5 volts before we apply it to the load. It allows us to set the function generator up. It allows us to set the offset at this point right here. At this point right here, it allows us to set this whole system up until we connect it to the load. Well, there you go. There you go. Oh, the totem pole circuit right here. We have plus 15 volts DC up here at the collector of the NPN transistor, and we have minus 15 volts DC down here at the collector of the PNP transistor. Afternoon all. Here we are at the house. In a little bit I'm going to have to go out and water the herbs and fill up the bird feeders, but for the time being, let's talk about our circuit to test that IGBT. Here is my box that I built for offset adjust. Now I use screws to clip onto. Here is plus VCC. It is tied to an external power supply providing plus 15 volts DC. That same external power supply, ground, is connected to this point right here. And this point right here, minus VCC, is tied to minus 15 volts DC. And that powers up our operational amplifier circuit inside that box. The Victor function signal generator provides, I've got it set to a plus 5 volt and minus 5 volt square wave on its output, ground being down here on the black wire, the frequency out on the red wire. The frequency output of the Victor function signal generator is fed to the frequency input of my offset adjust circuit. The black wire ground of that function generator goes to ground of this circuit right here. Now these two grounds, this ground here and the ground of the external power supply internally to my circuit, they are tied together. So this point and this point are connected. The offset adjusted frequency is applied to our circuit at this point right here, and I can adjust that offset above and below ground with this potentiometer right here. Now between the amplitude and the offset adjust, the amplitude of the Victor function generator and the offset adjust of our circuit right here, I have set the output to plus 5 volt peak square wave. Let's take a look at the next page. The output of our offset adjust circuit of a 5 volt peak square wave is applied to the anode of the LED input optocoupler, whose cathode is connected back to ground. We have a current limiting resistor of 560 ohms. So that when this point right here is at 0 volts, this LED is turned off. There's no current flow. And photons are not emitted into the base of this phototransistor. So it is not in saturation. It's not conducting. When this point right here goes to 5 volts peak, now we have current flow through this input LED inside that optocoupler, part number CMY17-2. And photons are emitted into the base of this phototransistor. And now, current from the plus 15 volt DC power supply flows through the collector base emitter junction. Oh, somebody's calling me. So now, current from the plus 15 volt DC power supply, this is an external power supply, isolated from ground on the low voltage supply. Here's our high voltage ground right here. Current flows from that power supply through the collector base emitter, through this 20 kilo ohm resistor into the base emitter junction of this tip 121 NPN transistor. And when this transistor is in saturation, because we are applying that voltage and current to the base emitter, we have 0 volts right here at the collector. So the gate of the IGBT is turned off. When this input is turned off, no current flows through the input LED, this photo transistor is turned off and no current flows into the base emitter junction of that tip 121, and it is not driven into saturation at that point. So now this same power supply plus 15 volts DC, we have current flows through this 1 kilo ohm resistor into the gate emitter junction of that IGBT, and that IGBT is turned on. It conducts. Let's take a look at the last page. We're almost there. Almost there. Hold on, folks. Don't get impatient. Here we go. This is the high voltage section. Over here is our IGBT, part number CM600HA 28H, manufactured by PRX. Now you'll notice here's the collector and emitter of that IGBT. And in the collector circuit, I have a light bulb load of 100 volts, 100 watts. Over here is the variac. This is a variable AC source. I have that plugged into 120 volts AC single phase, plugged into the wall. The output of the variac is connected to this bridge rectifier, and the bridge rectifier is creating the DC bus for this circuit right here. When I increase this AC voltage right here, the DC voltage increases. We saw that in the video. To filter the DC voltage for the bus, for the high voltage, I have two series 3300 microfarad 450 volt capacitors in series right here. The light bulb intensity increases as we raise this voltage right here with this variac. I only went up to, what was it, 100 volts peak at this point right here, and we saw that on the oscilloscope. There you go. That I think I've got it all. I think that's everything. I'm pretty sure that's everything. If I missed something, let me know in the comments. I'll try to get back to you. Well, we're real busy here. There's never a day goes by that we ain't got something to do. So if I don't get back to you, that's why. Let's go in the backyard. We'll water the herbs. Got some basil, chamomile, and some chives back there. We'll fill up the bird feeders, and we'll get ready for another day when the sun comes up. I hope y'all's doing okay. Things has gotten pretty bad here, and we're starting to buckle under the load, so if I disappear for a little while, you'll know why. I always appreciate it when you come over. Thank you very much for being there. I really appreciate who you are. You're good folks. We'll see you next time.